close your eyes and let yourself settle into comfort. Tonight, we're going to drift together through something quiet and ancient. A journey through time so deep that the years dissolve into something dreamlike. Millions upon millions of them, stacked like layers of soft sediment, each one holding secrets that have been resting in darkness for longer than we can truly imagine. There's something peaceful about deep time, the way it makes our worries feel small, the way it reminds us that the earth has been here, breathing and changing long before we arrived, and will continue long after we're gone. 66 million years ago, the world transformed, not through anger or violence, but through natural forces that have always shaped this planet. An asteroid arrived from the depths of space, and when it touched the Earth, everything changed. The world that had been simply became something new. And in the quiet aftermath, as dust settled and time moved forward as it always does, life found a way to continue. Small creatures emerged from shelter, plants returned to the soil. The earth remembered how to heal. But here's what makes this story so gentle, so dreamlike. We can only see fragments of what happened. Between the moments we understand, there are gaps, long, peaceful stretches of time where the fossil record goes quiet, and we're left to imagine what those ancient days were like. Tonight, we'll explore those quiet spaces together, the epochs that science can only partially see, the millions of years that rest between the fossils, like silence between musical notes. You don't need to remember any of this. Just let the rhythm of deep time carry you wherever you need to go. Let's begin. 66 million years ago, something arrived from space, an asteroid 6 miles across, traveling through the cosmic dark for perhaps billions of years before its path intersected with Earth's. When it touched down in what we now call the Yucatan Peninsula, the impact created a crater that still rests beneath the ocean and sediment, a place called Chicxulub. From above, if we could see through water and stone, we would observe a circular impression 93 miles wide, a gentle depression in the planet's surface, now softened by time. The impact released tremendous energy, and that energy moved through the Earth's systems in ways that changed everything. Debris rose into the atmosphere, not just dust, but millions upon millions of tiny particles that would drift in the upper air for months, perhaps years. They created a kind of veil between the earth and sun, dimming the light that reached the surface below. And in that dimness, the world began to cool. The plants felt this change first. Sunlight is everything to a plant. It's breath and food and life itself. When the light dimmed, photosynthesis slowed, and gradually, across the world, many plant species began their quiet, exit from Earth's story. The fossil record shows the transition through pollen. In rock layers from before the impact, we find diverse pollen from countless flowering plants. In layers after, that diversity fades. Many species simply step back from the record, making room for what would come next. As plants transformed, so did the animals that depended on them. The great herbivores of that time, the horned dinosaurs and duck-billed hadrosaurs that had roamed in peaceful herds for millions of years, found their food sources changing. Over time, their populations dwindled. Generation by generation, fewer remained. And eventually, they too stepped back from Earth's story, leaving behind only their bones pressed into stone. The predators followed the same gentle path. Tyrannosaurs and raptors, those magnificent hunters that had evolved over 100, almost a million years, found their prey becoming scarce. They lingered for a time, but the world was shifting toward something new, something smaller, something that would favor different strategies for survival. About 75% of species that existed before the impact would eventually fade from the fossil record. This happened over what geologists call an instant, though in their time scale, that might mean thousands of years. Enough time for many generations to live and pass. Enough time for ecosystems to gradually shift and resettle. Between the Cretaceous and Paleogene periods, there's a thin layer of clay. It appears in rock formations all around the world, usually just a few centimeters thick. This layer contains iridium, an element rare on Earth's surface but common in asteroids. If you were to place your finger on this boundary in a cliff face, you'd be touching the moment of transition. Above, one world, below, another. But here's something gentle to consider as you drift. Not everything faded. Some creatures persisted, and their survival had nothing to do with being fierce or powerful. It had everything to do with being small, flexible, and in some cases, simply fortunate. Small mammals survived, creatures no bigger than modern rats, who had spent millions of years living quietly, largely unnoticed. They could shelter underground during harsh times. They could survive on seeds and insects and whatever the changing world provided. When the larger animals gradually departed, these small survivors found themselves in a world full of possibility. Birds survived too, though only certain kinds. The fossil record suggests that smaller ground-dwelling birds who could eat seeds and adapt to changing conditions made it through. These would eventually give rise to the 10,000 bird species we know today. But in those early days of recovery, they were just small populations, quietly persisting in a transforming world. Let your breathing slow now, if it hasn't already. Crocodiles and turtles also persisted. These ancient creatures had a gift for patience. They could go long periods without food, could tolerate conditions that would challenge other animals. Their lineages continued forward through the transition, carrying ancient wisdom in their blood. In the oceans, many fish species and sharks continued as well. The marine world experienced changes, certainly, but the ocean has a way of softening extremes. Water holds heat and cold differently than air. It buffers. It protects. Many ocean dwellers found they could adapt to the slowly shifting conditions. Now, here's where the story becomes dreamlike. The fossil record from immediately after the impact is remarkably sparse. We're looking at one of the most important transitions in Earth's history, and we can only see fragments of what occurred in the years and decades that followed. This isn't a failure of science. It's simply the nature of fossilization. Creating a fossil requires very specific conditions. A creature must pass away in just the right place, be covered by sediment at just the right speed, be preserved by just the right chemistry over millions of years. During the chaotic time after the impact, these conditions were rare, and there's another reason for the gaps. After the transition, there simply weren't as many creatures present to become fossils. When populations become small, scattered in whatever refuges still support life, they leave fewer traces behind. So we have this peaceful mystery. We can see the world before. We can see the thin layer marking the moment of change. And we can see what emerged millions of years later. But the transition itself, those crucial years of healing and adaptation, rest mostly in shadow. You don't need to hold on to any of this information. Just let it wash over you, gentle as waves. What we do know is that the world that emerged was different. The climate slowly stabilized. New forests grew, with different species adapted to different conditions. The surviving animals gradually explored the empty spaces, developing new forms, new ways of being. Some researchers point to volcanic activity that was already present before the impact. In what is now India, massive volcanic systems called the Deccan Traps were releasing gases into the atmosphere for hundreds of thousands of years. These may have already been shifting the climate, creating stress that made the impact's effects more profound. It's likely that many factors work together, creating the conditions for transformation. But here's what makes this ending also a beginning. Those small mammals that survived inherited an empty world, a world without dominant predators, a world full of ecological niches waiting to be filled. Within a few million years, these rat-sized survivors had grown and diversified into forms that would have seemed impossible before. Some became predators, others became herbivores, Some learned to climb trees, others learned to swim. One particular lineage of these survivors would, over vast stretches of time, eventually evolve into primates, and millions of years after that, into apes, and eventually into us. Every human who has ever lived is descended from those small, patient mammals who found shelter during Earth's time of transition 66 million years ago. We exist because they persisted. Let your body sink deeper into comfort now. As we stare at that thin layer of clay in the rock record, as scientists try to understand what happened in the years that followed, we're reminded of something peaceful. Some of Earth's most important moments rest in spaces we cannot fully see. The world transformed, the world healed, and most of the details have dissolved into time. This is just the first gap we'll explore tonight. The first place where Earth's story becomes gentle and unclear. So the impact occurred. The world shifted. The dust settled slowly back to Earth. And then what? This is where the story should become clearer, you might think. Life begins again. New species emerge. We should be able to watch evolution unfold like pages in a book. But we cannot, because the Paleocene, those first 10 million years after the transition, is when the fossil record becomes especially quiet and dreamlike. Here's what we understand about this time. Small mammals who had survived began to explore their new world. These were tiny creatures, most no bigger than rats or shrews. They had spent 160 million years living quietly in the shadows of dinosaurs, evolving to be small, to be unnoticed, to move in darkness. Then suddenly, the dinosaurs were gone, and the world felt vast and open. If your eyes are growing heavy, that's perfectly natural. Imagine being one of those small mammals. Your entire evolutionary history has been about staying hidden, staying small. Then one day, you emerge from your burrow, and the predators that had shaped your ancestors' lives for millions of years are simply absent. For the first time in your species' existence, nothing is hunting you. What would you do? You would expand. You would explore. You would grow. And that's precisely what happened. Within the first million years of the Paleocene, mammals began getting gradually larger, not dramatically at first, but measurably. Species that had been mouse-sized began producing descendants that were rabbit-sized, then dog-sized. The evolutionary pressure that had kept them small for so long had lifted. But here's where the fossil record begins its gentle mystery. We should be able to watch this transformation step by step, track these small survivors gradually becoming larger, spreading into new environments, developing new adaptations, and we can sort of, but only in fragments, only in pieces so scattered across time and space that scientists spend their careers trying to understand how they connect. Let your jaw relax. Let your shoulders drop. You're doing wonderfully. There's nowhere you need to be but here, drifting through these ancient, peaceful mysteries. Consider the question of timing. How quickly did mammals actually grow during the Paleocene? Some fossil sites suggest relatively rapid change, with size increases visible within a few 100,000 years. Other sites show much slower, gentler transformation over millions of years. Which is correct? We don't know with certainty because we don't have continuous records from enough locations. We have snapshots, moments frozen in stone, separated by hundreds of thousands of years of quiet time. It's like watching a film where most of the frames have been removed. You see an opening scene, dinosaurs everywhere, then darkness. Next frame, they're gone, and small mammals are present. Darkness again. Next frame, those mammals are larger, more diverse. Another long darkness, and when the light returns, you see creatures that look entirely new. The gaps aren't frustrating. They're simply part of the mystery, part of what makes deep time so dreamlike. During this time, the planet itself was healing and transforming. Forests were gradually returning, not the same forests that existed before. Those had passed away, but new forests, growing from seeds and spores that had endured. Ferns were among the first plants to reappear. They reproduce through spores that can survive harsh conditions, lying dormant until the time is right. Within a few thousand years, vast fern meadows covered what had been bare landscapes. Then came the flowering plants, the angiosperms. They had been relatively minor before the transition. Afterwards, they flourished, becoming the dominant plant form across most of the planet. This created entirely new ecosystems, and mammals evolved to live within them in ways that would have been impossible in the old world. Some mammals became browsers, eating leaves and tender shoots. Others became frugivores, feeding on the abundant fruits produced by flowering plants. Still others became hunters, gentle predators, adapted for the new world's rhythms. But we're missing most of the details of how these transformations occurred. We know these adaptations happened because we find fossils that clearly show them. Teeth designed for grinding plants, limbs adapted for climbing, bodies built for moving swiftly across open ground, but the intermediate forms, the species that bridged the gap between the early survivors and these specialists, are largely absent. Part of why we're missing so much is simply the nature of fossilization. It requires very specific conditions. A creature passes away and must be buried quickly before decay or scavengers can scatter the remains. It must stay buried in sediment that eventually transforms to stone. Then Millions of years later, that stone must be exposed by erosion at just the right moment for someone to find it. Each step is unlikely. Most organisms that ever lived never fossilized. They simply returned to the earth, leaving no trace. But the Paleocene seems to have been particularly challenging for fossil preservation. The environmental conditions following the transition created situations that made fossilization less likely in many regions. Sea levels fluctuated, climate zones shifted. The stable environments where fossils form best were constantly changing. So we're left with scattered evidence. A fossil here, another 1,000 miles away. A third separated from the first by 2 million years. Scientists try to connect these into a story, but the connections require gentle speculation. And then there are creatures that appear in the Paleocene record, thrive for a while, and then simply fade away. Evolutionary experiments that didn't continue forward. Lines that ended without descendants. Consider the multituberculates. These were mammal-like creatures that had existed since the time of dinosaurs. They had been present for over 100 million years, making them one of the most enduring mammal groups in history. In the early Paleocene, multituberculates flourished. They grew larger, spread into many environments, developed varied adaptations. Fossil evidence suggests they were everywhere, possibly the most common mammals on Earth during this time. Then, sometime during the Paleocene or early Eocene, they gradually faded from the record, all of them, every species. We don't know why. We don't know exactly when. They're simply present in older rock layers and absent from younger ones. Let your breathing deepen in and out, slow and steady. 120 million years of evolutionary success, and then a quiet exit during Earth's recovery period. Not a failure, just a natural conclusion. All things pass in time. If sleep is calling to you now, you can answer. You don't need to hear every word. Let yourself drift naturally whenever feels right. The Paleocene is full of these gentle mysteries, mammals that evolved, thrived briefly, then stepped back from the story. Creatures that would seem unusual to modern eyes. Early plant eaters that don't clearly connect to any living mammals. Ancient hunters that weren't ancestors of modern predators. Each represents millions of years of evolution that led to its own unique conclusion. Meanwhile, the climate was doing something noteworthy. For most of the Paleocene, temperatures were relatively moderate, not Ice Age cold, but cooler than the late Cretaceous had been. The planet was finding its new balance, slowly and patiently. Then, about 56 million years ago, something shifted. Global temperatures began to rise, not over millions of years, but over thousands, perhaps even faster. This event is called the Paleocene-Eocene thermal maximum, often shortened to PETM. Average global temperatures increased by several degrees in what feels to geologists like an instant. The effects rippled across the world. Ocean chemistry shifted on land. Entire forests migrated toward the poles, following the temperature ranges where they thrive best. And mammals, those survivors who had been steadily diversifying for 10 million years, faced new conditions to adapt to. We should be able to see clearly how they responded, watch them adjust, migrate, develop new strategies for living in a warmer world, and we can see some of this. But as always, the fossil record from this period is incomplete. We have excellent snapshots from certain locations, but vast regions have no preserved record from this time at all. So we know the warming happened. We know it caused evolutionary changes. We know mammals responded by developing smaller body sizes in many cases, an adaptation to heat stress. But we can't see the complete picture, can't track how changes in one place connected to changes somewhere far away, can't identify every innovation that emerged in response to the warmth. It's like trying to understand a global event while only having information from 3 cities. You can see that something significant occurred. You can identify some patterns, but you're missing most of the story, most of the connections, most of the subtle details that would help you truly understand. And that's the fundamental nature of the Paleocene. We know this was one of the most important periods in mammalian evolution, the time when our distant ancestors transformed from tiny survivors into diverse creatures, beginning to fill many roles in their ecosystems. The 10 million years that set the foundation for everything that came after, including, eventually, us. But we're viewing it through fragments, catching glimpses, missing the crucial moments. Scientists have been working on this mystery for over a century. Every year, new fossil sites are discovered, new species are described, new connections are proposed. The picture becomes slightly clearer, slightly more detailed, but the gaps remain, and some of them may never be filled. Some of the species that evolved during the Paleocene may have lived in environments that simply don't preserve fossils well. Mountain regions, upland forests, areas that have since been completely transformed by plate tectonics or eroded away by millions of years of wind and water. Those species existed. They mattered. They contributed to the path that led to modern mammals. But we'll never see their details. Let your mind rest now. What we're left with is an outline, a gentle sketch where there might have been a detailed painting. We know mammals diversified. We know forests returned. We know the climate eventually warmed. We know some evolutionary lines continued while others naturally concluded, but the precise mechanisms, the individual stories of adaptation, most of those rest in peaceful mystery. The Paleocene represents Earth's recovery period, but it's also one of paleontology's most beautiful mysteries. A time when everything was transforming, and we can only see pieces of how it happened. Now, let's drift forward to something even more dreamlike. The world after the Paleocene became something extraordinary. We're speaking of an Earth so different from what we know that it might as well have been another planet entirely. And yet, it was this same Earth, just wearing a different face. The Eocene epoch, from 56 to 34 million years ago. The name means dawn of the recent, which is somewhat ironic, because the conditions during this time were unlike anything recent. This was the last period when our planet was a true greenhouse world. No ice existed anywhere, not at the poles, not on mountains, nowhere. The entire planet was warm. Imagine standing in what would one day become Alaska. But instead of cold and tundra, you're surrounded by subtropical forests. Palm trees swayed gently in the warm Arctic breeze. The temperature hovers around 70 degrees Fahrenheit all year round. During the Eocene, seasons, as we know them, didn't really exist. The global climate was so warm that temperature differences between the equator and the poles were minimal, perhaps 20 degrees of variation, instead of the 100-degree differences we see today. Alligators lived in rivers where Wyoming now sits. Ancient primates climbed through forests that covered the American Midwest. The Arctic Ocean was warm enough to swim in comfortably. Sometimes the surface waters reached 70 to 75 degrees Fahrenheit, warmer than many modern beaches. Try to imagine that world as you drift. Palm trees in the Arctic, warm oceans at the poles, an Earth so gentle and tropical that winter never came. But here's something curious. We don't fully understand why the Eocene was so warm. Atmospheric carbon dioxide levels were certainly higher than today, perhaps 2 or 3 times current levels. But when scientists run climate models with those CO2 levels, the poles still come out cooler than the fossil evidence suggests they actually were. There's something we're missing. Some natural feedback mechanism in Earth's climate system that we haven't fully understood yet. Let any tension in your body dissolve now. Your forehead smooth, your eyes resting gently. You're safe here in this moment, drifting through ancient peaceful times. This warm period lasted 22 million years. For perspective, that's longer than the entire span from the asteroid impact to the beginning of the Eocene itself. 22 million years of unbroken warmth. Time for life to fully adapt to this tropical world and develop into forms we can barely imagine now. The mammals of the Eocene were wonderfully strange. There were early versions of groups we'd recognize, small horse-like creatures the size of dogs, early whales that still had legs and could walk on land, ancient primates beginning to experiment with life in the trees, but there were also entirely new groups that have no modern descendants, evolutionary experiments that flourished for millions of years and then naturally concluded. The creodonts, for instance, these were the main predators of the early Eocene, filling roles similar to modern big cats and wolves. But they weren't related to today's carnivores at all. They represented a completely different approach to being a hunter. Some were large, bigger than modern lions. Others were small and quick. They thrived for millions of years before gradually fading from the record around 35 million years ago, replaced by the ancestors of modern carnivores. We don't know exactly why creodonts faded while other carnivores continued. We just know that over time, one group was replaced by another. Millions of years of evolutionary history came to its natural end, and new stories began. Or consider the Brontosaurus. Imagine something like a rhinoceros, but different. These massive plant eaters had elaborate Y-shaped horns and could grow to 8 feet tall at the shoulder, weighing 4 tons. They were everywhere during the Middle Eocene, living across North America and Asia. Then, around 34 million years ago, they quietly exited the story. The entire family of Brontosaurus, dozens of species, all gone within what seems like a very short time geologically. The fossil record shows them present one period, then absent the next. What happened? Climate shifts, changes in available food? We can only wonder gently. Now, here's something peaceful to consider. The Eocene should have left us an incredible fossil record. Warm, wet conditions usually mean abundant life and good preservation. But instead, the Eocene fossil record has many quiet spaces, places where we'd expect to find thousands of specimens, but have only a few. Crucial transitional periods where we'd love to see how species evolved, but find very little. Part of this is geology working in its own time. The Eocene was a period of intense geological activity. Continents were moving, creating new mountain ranges and closing ancient seas. India was slowly connecting with Asia, pushing up the Himalayas. The Atlantic Ocean was widening, separating North America and Europe. All this movement could bury or transform fossil sites, making them difficult or impossible to access now. But it's also the environment itself. Tropical rainforests, which covered huge portions of Eocene Earth, are actually quite poor at preserving fossils. The heat and moisture cause bodies to decompose very quickly. The acidic soils can dissolve bones. The constant growth and decay of vegetation churns the ground. Modern rainforests are among the most biodiverse places on Earth, yet they produce very few fossils. The Eocene rainforests were likely the same, full of life that left almost no trace. So we're left reconstructing an entire epoch from scattered clues. A jawbone here, a tooth there. Occasionally, if fortune smiles, a nearly complete skeleton. From these fragments, we try to understand a world utterly different from our own. You're drifting beautifully now. There's no need to hold on to any of these details. Just let them flow through your mind like water, gentle and soothing. The early primates show us how incomplete our picture is. Somewhere during the Eocene, the ancestors of monkeys, apes, and eventually humans diverged from the ancestors of lemurs and lorises. This is one of the most important splits in primate evolution, the beginning of the line that would, after many millions of years, lead to us. And the fossil record for this transition is remarkably sparse. We have early Eocene primates that look somewhat lemur-like, small tree-dwelling creatures adapted for tropical forests. We have Middle Eocene primates that show some features suggesting they might be closer to the monkey and ape line. And we have later primates that are clearly on the path toward modern monkeys and apes. But the transitions between them, the species that show the actual steps of evolution, mostly absent, resting in those quiet millions of years of rainforest that preserved almost nothing. There's a gap in our understanding millions of years wide. We can't see clearly how the features that make our primate lineage unique first developed. Forward-facing eyes, grasping hands, larger brains, all the characteristics that would eventually contribute to humans. The evidence rests peacefully in mystery. This pattern repeats across many mammal groups. The evolution of horses from small forest browsers to larger grassland grazers. The development of whales from land-dwelling ancestors to fully aquatic mammals. The origin of bats, the only flying mammals. In each case, we have pieces of the story, but the connecting pieces remain hidden. We have early Eocene fossils of bats that are already fully developed for flight. This suggests they evolved their flying abilities millions of years earlier. But we don't have fossils of their flightless ancestors. That part of the story remains in shadow. Then, 34 million years ago, something significant began. The greenhouse world started to shift, not instantly, but relatively quickly in geological terms. Within less than 1 million years, global temperatures dropped notably. For the first time in over 20 million years, ice sheets began forming in Antarctica. The tropical forest that had covered so much of the planet gradually retreated toward the equator, and many species began their natural exit from the story. We know this transition happened. The evidence is clear in the rocks and in the fossils, but we don't completely understand why. The leading idea involves changes in ocean currents as continents continued to drift. The Drake Passage between South America and Antarctica slowly opened, allowing new current patterns to form this isolated Antarctica, preventing warm water from reaching it, allowing it to cool and freeze. The formation of Antarctic ice sheets created a natural feedback. Ice reflects sunlight back into space, which cools the planet further, creating more ice. A gentle cycle of transformation. But the timing doesn't quite match up perfectly. Some evidence suggests cooling began before the passage fully opened. Other evidence shows brief, warm periods within the overall cooling trend. The transition wasn't smooth, it was complex, with many factors working together. What we do know is that this shift fundamentally changed which animals continued and which ones concluded their stories. The creodonts exited, the brontothrus faded. Dozens of other mammal families that had thrived for millions of years came to their natural ends. In their place, new groups emerged. Ancestors of many modern mammals, animals adapted for the cooler, more seasonal world that was arriving. We don't fully understand the pattern of who continued and who didn't. Some groups disappeared entirely. Others persisted, but in smaller populations. Still others expanded as conditions changed. Understanding why is difficult because we're missing so much connecting information. Let yourself sink even deeper now. The Eocene represents one of the most mysterious stretches in our planet's history. 22 million years of warmth that produced life forms we can barely imagine, then a transition to something cooler. Somewhere in those Eocene forests, our own evolutionary lineage was beginning to develop the characteristics that would eventually lead to humans. Enhanced vision, hands adapted for grasping, slightly larger brains. The foundations of human evolution were being laid in those ancient trees, and we can only see it in fragments. The Earth has kept most of those details private, leaving us with questions that may never find complete answers. And that's okay. There's something peaceful about not knowing everything, about letting some mysteries remain mysterious. As we drift further forward in time, we come to periods that should be clearer. The Oligocene and Miocene epochs, spanning from 34 million to about 5 million years ago. Nearly 30 million years of Earth's history that should be well documented. These are, after all, relatively recent times in geological terms. But once again, we find ourselves looking at a record filled with quiet spaces. During this time, the planet continued its gentle cooling. Antarctica, which had been tempered and forested just a few million years earlier, became completely frozen around 34 million years ago. Within a relatively brief period, it transformed from a continent with rivers and trees into a land of ice. This transformation should be documented in countless fossil sites across the globe, but instead, we have gaps. Large, peaceful gaps where entire ecosystems seem to step back from the record with no clear transition. The cooling didn't stop with Antarctica. Over the next 30 million years, global temperatures continued their downward drift. The hot, jungle-covered world that had dominated Earth for hundreds of millions of years was slowly, naturally concluding. And something new was emerging, grasslands. Now, grasslands might not sound particularly dramatic, but this was one of the most significant ecological transitions in Earth's history. For most of the age of mammals, the planet had been dominated by forests. Dense, vertical ecosystems where success meant being able to climb, to live among branches. Then, gradually, huge portions of those forests transformed into open spaces, endless plains of grass stretching to the horizon. This should be beautifully documented in the fossil record. The shift from forest to grassland would have touched every animal's life. New species would have emerged to thrive in open spaces. Old species would have adapted or gracefully exited. We should see this transformation layer by layer, species by species. But we don't. What we have are snapshots, brief windows into this 30 million year period separated by enormous gaps. We have forest ecosystems from the early Oligocene, then millions of years of quiet in the record. Then suddenly, in the late Miocene, we see vast grasslands with completely different animal communities. The transition between them, the actual process of transformation, is largely hidden from view. Let your whole body feel heavy now, sinking into comfort, your breath slow and natural. If sleep wants to take you, welcome it gently. And nowhere is this gap more significant than when it comes to our own ancestors. Because somewhere during the Oligocene and Miocene, something remarkable happened. Apes evolved, not just any apes, but the lineage that would eventually, after many millions of years, lead to humans. This should be intensely studied, deeply understood. This is when our family tree began its unique branching. Instead, what we have is what scientists gently call a substantial gap in the fossil record. Here's what we think happened, based on the scattered evidence we found. Around 25 million years ago, during the Oligocene, primitive apes started appearing in Africa. These weren't like modern apes. They were smaller, more monkey-like, still spending most of their time in trees. But they had certain characteristics that marked them as apes rather than monkeys. They were our ancestors, the beginning of our line. Then the fossil record becomes very quiet. For millions of years, we have almost nothing. A tooth here, a jaw fragment there, but no complete remains. No clear evolutionary sequences, no way to track how these primitive apes were changing. It's like watching a film where most of the frames are missing. You can guess what's happening, but you're imagining most of it. When the record picks up again in the middle Miocene, around 15 million years ago, everything has changed. Now we have multiple ape species spread across Africa, Europe, and Asia. Some are small and graceful. Others are massive, weighing hundreds of pounds. Some are clearly adapted for life in trees. Others show early signs of adapting to ground-dwelling life. The diversity is beautiful, and the evolutionary relationships between them are nearly impossible to untangle because we're missing the connecting fossils. Scientists call these ghost lineages, evolutionary lines that must have existed, that had to have existed based on genetic and anatomical evidence, but which left almost no fossil trace. The mathematics of evolution tells us they were there. DNA analysis of modern apes confirms they existed, but the rocks remain silent about their details. Think about what this means as you drift. For roughly 10 million years, during a crucial period when apes were diversifying and spreading across 3 continents, we have maybe a few dozen partial specimens total. We have better fossil documentation of dinosaurs from 100 million years ago than we do of our own ancestors from just 20 million years ago. Why? What became of all those fossils? Part of the answer is geology. The Oligocene and Miocene were periods of intense geological activity. Mountain ranges were forming. India was continuing its slow collision with Asia, pushing up the Himalayas higher and higher. All this geological movement was creating dramatic landscapes, but it was also transforming or destroying the sediments where fossils might have formed. Fossilization requires very specific, stable conditions. You need the right kind of sediment, the right water chemistry, the right rate of burial, and you need all of that to remain undisturbed for millions of years. But during the Oligocene and Miocene, vast areas were being uplifted, eroded, folded, and fractured. Sediments that might have contained fossils were being transformed as quickly as they formed. The climate changes made things more challenging as well. This was a period of significant global cooling, but that cooling wasn't smooth. It was punctuated by sudden shifts, periods of rapid change that could transform entire ecosystems in just a few thousand years. These rapid transitions were difficult for fossil formation. Here's why. Fossils form best in stable environments. Lake bottoms where sediment accumulates year after year. River deltas where regular flooding gently buries remains in mud. Stable forests where fallen creatures are slowly covered and preserved. But when the climate is shifting rapidly, these stable environments disappear. Lakes dry up. Rivers change course. Forests transform into grasslands, which don't preserve fossils nearly as well. Let your mind wander now, gently and without effort. During the Oligocene and Miocene, Earth was experiencing some of the most dramatic climate variations in mammalian history. Temperatures would drop, then stabilize, then drop again. Rainfall patterns would shift, turning wet regions dry and vice versa. These fluctuations created an ever-changing landscape, beautiful but unstable. None of the environments lasted long enough to preserve extensive fossil records. You're doing beautifully. Let every muscle soften. Let your thoughts become like clouds, drifting by without needing to hold on to them. And it wasn't just our ancestors that became scarce in the record. Entire families of animals evolved during this period with almost no connecting fossils. Modern horses, for instance, we know they evolved from small multi-toed forest dwellers into large single-toed plains runners during the Miocene. This required massive changes to their anatomy, their digestion, their behavior, everything. In North America, the fossil record of horse evolution is actually quite good. We can track the changes step by step, see how they gradually adapted to life on open grasslands. But in Eurasia and Africa, where horses also evolved during the same period, the record is fragmentary at best. Whole branches of the horse family tree appear and disappear with no clear ancestry, no obvious connections. The same pattern repeats across many mammal groups. Modern elephants evolved during the Miocene from smaller ancestors, but the transitional forms, the species that link early proboscideans to modern elephants, are mostly missing from the record. We have the end points, but the journey between them is largely hidden. Modern big cats evolved during this period as well. Lions, tigers, leopards, all emerging from a common ancestor that lived sometime in the Oligocene or early Miocene. But we have very few fossils showing how this diversification happened. The earliest clear lion fossil is only about 3.5 million years old. But genetic analysis tells us lions split from other big cats at least 10 million years ago. Where are those missing 6 million years, resting peacefully in mystery? Even modern primates, our closest relatives, show the same pattern. Gorillas, chimpanzees, orangutans, all these species have ancient origins stretching back into the Miocene. But their fossil records are essentially non-existent. We have more fossil evidence of extinct ape species that aren't closely related to anything alive today than we do of the direct ancestors of our closest living relatives. This creates an interesting situation. We know more about evolutionary experiments that didn't continue forward than we do about successful lineages. The species that concluded their stories often left better fossils than the ones that persisted. And the grassland transition makes everything more challenging because grasslands are actually quite poor at preserving fossils compared to forests and wetlands. In a forest, when an animal passes away, it often falls into water or gets buried in soft, organic, rich soil. Good conditions for fossilization, but on a grassland, remains are exposed to scavengers, weather, and natural decay. Within weeks, most traces are scattered and returned to the earth. Only under very specific circumstances, like being covered by a flash flood or fallen into a sinkhole, do they have any chance of preservation. So, as forests gave way to grasslands during the Miocene, the probability of fossil preservation dropped significantly. And this happened exactly when apes were undergoing their most important evolutionary developments. But here's something to consider gently as you drift. It's not just that we're missing fossils. We're probably missing entire species, entire evolutionary experiments that emerged, persisted for hundreds of thousands of years, and then naturally concluded, leaving no trace we've discovered. Genetic analysis of modern apes suggests there should have been dozens of ape species living during the Miocene. Different lineages branching and evolving, adapting to various environments. The genetic diversity we see today could only have come from a much larger ancestral population. So where are they? How many species evolved and exited during those 30 million years without leaving a single fossil we can find? These ghost lineages are significant precisely because we know they must have been real. But we can't see them, can't study them, can only acknowledge their existence as gaps in our understanding. And those gaps have real meaning for understanding human evolution, because somewhere in those missing millions of years, something happened that set our lineage on its unique path. Somewhere between 25 and 5 million years ago, the ancestors of humans diverged from the ancestors of other apes. They developed characteristics that would eventually lead to walking upright, using tools, developing larger brains. All the features that make us human. But we don't know when. We don't know how. We don't know what environmental circumstances encourage these changes or what intermediate forms connected primitive apes to the first recognizable human ancestors. The Oligocene and Miocene should answer these questions. Instead, they hold the answers gently, privately. What we're left with is thoughtful speculation built on fragments. We can suggest that climate change played a role, that the spread of grasslands created new circumstances that favored certain adaptations, That competition between ape species drove innovation, but we're imagining building elaborate possibilities on foundations of sand, hoping that someday someone will find the fossils that fill in these peaceful gaps. Until then, these epochs remain the quiet middle chapters, the crucial period between the ancient world of forests and the modern world of grasslands, the time when our ancestors transformed from tree-dwelling apes into something beginning to look unique. The 30 million years that should explain so much, but instead rest in gentle mystery. Let yourself be completely at ease now. Your body is safe. Your mind can wander wherever it wishes. Sleep is welcome whenever it arrives. Now we come to a period that should be the clearest of all, the Pliocene epoch. 5 to 2.6 million years ago, the time when our ancestors stopped being apes and began becoming human. This is recent, practically yesterday in geological terms. Some Pliocene animals are still alive today. Elephants, rhinoceroses, many bird species, and yet we have enormous gaps in our understanding of this period. Gaps that seem, at first, surprising. Here's something interesting to contemplate as you rest. We actually have better, more complete fossils of dinosaurs that lived 66 million years ago than we do of human ancestors who lived just 100,000 years ago. A Tyrannosaurus rex that passed away 66 million years ago. Museums can display skeletons that are 70, 80, sometimes 90% complete. But a Neanderthal from 40,000 years ago? We're fortunate if we find a jawbone and a few teeth. The Denisovans, an entire human species that lived across Asia until perhaps 30,000 years ago. We found exactly one finger bone, a handful of teeth, and a piece of skull. That's everything we have from an entire species that spread across millions of square miles and persisted for hundreds of thousands of years. From these few fragments, scientists have mapped their genome, figured out they interbred with modern humans and Neanderthals, determined they adapted to high altitudes, all from a finger bone. In 2004, scientists discovered Homo floresiensis, sometimes called the hobbits, on an Indonesian island, a completely unknown human species that survived until perhaps 50,000 years ago. We had no idea they existed. Then suddenly, we're finding remains of 3-foot-tall humans with small brains who somehow made sophisticated stone tools. In 2015, we found Homo naledi in South Africa, another completely unknown human species, thousands of bones in a single cave system. And we still aren't entirely certain how old they are. They might be 2 million years old based on their anatomy, or they might have survived until 130,000 years ago, living at the same time as early modern humans. How do we lose entire human species? These aren't microscopic organisms. These are large mammals with complex behaviors who made tools, used fire, cared for their communities. They should be well represented in the fossil record. But they're not. They're shadows. We know they existed only because of a handful of fortunate discoveries in caves and volcanic ash deposits. Let your breathing slow even more now, if it hasn't already. The conventional explanation is that the Pleistocene ice ages, which began about 2.6 million years ago, transformed most of the evidence. And this is partially true. For over 2 million years, massive ice sheets advanced and retreated across the northern hemisphere. At the peak of glaciation, ice up to 2 miles thick covered vast regions. That ice was like a continental sculptor. It shaped the land, carved valleys, ground rock into gravel, transformed everything in its path. When the glaciers finally retreated about 11,700 years ago, they left behind landscapes completely changed. Any sites where humans had lived, any evidence of populations in those regions was gently reshaped or carried away by meltwater. So that explains the gaps in the glaciated zones. But humans didn't just live under the ice. They lived in Africa, Asia, Australia, South America. Regions that were never glaciated. Where's the evidence from those areas? This is where the mystery deepens. Archaeological sites older than 50,000 years are extraordinarily rare, not just uncommon. Rare to the point of being exceptional. We can count on our hands the number of well-preserved sites from before 50,000 years ago. And most of those are caves, places where unusual conditions allowed preservation. Open-air sites, campsites, places where people actually spent most of their time. Almost nothing survives. During the Pleistocene, there were millions of humans living across multiple continents for hundreds of thousands of years. They were making tools constantly, creating hearths, processing food, building shelters. They should have left behind countless traces, even if 99% of those traces were naturally recycled by the earth. We should still be finding them regularly. But we don't. The archaeological record is sparse, scattered, full of long, peaceful gaps where we have essentially nothing. And then there's the megafauna extinction. Between about 50,000 and 10,000 years ago, the majority of large mammal species on Earth gradually exited the story. Woolly mammoths, mastodons, saber-toothed cats, giant ground sloths, cave bears. In North America alone, 34 genera of large mammals concluded their time on Earth. This happened right when humans were spreading across the globe. The correlation is clear. We arrived in new places, and the large animals gradually disappeared. But here's something interesting. We have almost no direct evidence of humans hunting these animals extensively. Yes, we have a handful of sites. Yes, We have mammoth bones with spear points, but we're talking about dozens of sites documenting the exit of hundreds of species across multiple continents. If humans hunted these animals to extinction, there should be thousands of sites, massive bone accumulations, processing areas where people harvested these animals generation after generation. Where are they? Most theories assume the evidence is missing because of natural processes. Sites in open areas were transformed by erosion and glaciation. The evidence existed, but time recycled it, perhaps. But the amount of missing evidence is substantial. You're drifting so peacefully now. Let any remaining thoughts dissolve like mist. You're safe, comfortable, exactly where you need to be. Then there's the sea level mystery during the ice ages, when glaciers held enormous amounts of water. Global sea levels were 300 to 400 feet lower than today. This exposed vast areas of continental shelf that are now underwater. The Bering Land Bridge between Asia and North America was thousands of miles of open grassland. The Indonesian archipelago was a single continuous land mass. The Persian Gulf was a river valley. These weren't marginal environments, they were prime locations. Coastal areas with access to both marine and terrestrial resources. Exactly the kind of places where human populations would naturally thrive. And we've lost all of it. When the glaciers melted and sea levels rose, hundreds of thousands of square miles of human habitation area went underwater. Not gradually, but sometimes quite rapidly. There's evidence of sudden sea level rise events where ocean levels jumped 10, 15, even 20 feet in just a few decades. Imagine watching the ocean advance inland by miles within a single generation. Everything built by previous generations slowly covered by water. That means the majority of human activity during the ice ages is now resting on the ocean floor, under sediment and marine growth, completely inaccessible to most archaeologists. We've done some underwater archaeology in shallow areas, and every time we find unexpected things. Submerged caves with Ice Age art, drowned river valleys with tools and remains, ancient shorelines with evidence of sophisticated cultures we hadn't known existed. But we've barely explored the surface of what's down there. The continental shelves represent millions of square miles of unexplored territory. We have better maps of Mars than we do of the Ice Age landscape sitting under a few hundred feet of water off our coasts. So, here's something to consider gently as you rest. What if we're missing more than just simple hunter-gatherer camps? This is a thoughtful question that's emerging in archaeological circles. The standard story says complex societies emerged only after the Ice Ages ended, only after agriculture was invented about 10,000 years ago. Before that, humans lived in small groups. no permanent settlements, no large-scale organization. But that story is based on the assumption that we have a reasonably complete archaeological record. And we're starting to realize we don't. We're missing enormous chunks of time and space. The gaps are so large that we genuinely cannot say with certainty what was or wasn't happening during the Pleistocene. Göbekli Tepe in Turkey has already shifted our understanding. Built 11,500 years ago by people who supposedly hadn't invented agriculture. It features massive stone pillars carved with sophisticated artwork, organized into complex circular structures that required coordinated effort by many people. This isn't supposed to exist according to the old models, but there it is, real and undeniable. And if Göbekli Tepe exists from right at the end of the ice ages, what else might have existed during the ice ages that we simply haven't found yet? What got covered by rising seas or reshaped by advancing glaciers? We don't know. We can't know. That part of the story rests in peaceful mystery. What we do know is this. The Pleistocene was a time of dramatic environmental change, repeated ice ages, and human populations pushed to the limits of adaptation. Each glacial advance, each climate shift would have affected populations, transformed landscapes, reset cultural development in affected regions. The humans who persisted were resilient, adaptable, creative, but they were also living through challenging times, knowing the climate could shift at any moment. Maybe they created sophisticated cultures that left no trace. Maybe they developed technologies built from materials that don't survive. Maybe they told stories and created art and organized themselves in complex ways we'll never discover. Or maybe they really were living simply, and we're just experiencing normal preservation challenges magnified by ice age transformations. The difficulty is that we're both too close and too far from this period. Too close to have the kind of geological preservation that helps with older fossils. Too far to have the kind of detailed archaeological record we get from more recent times. We're in a gap, a significant peaceful gap in the most important period of human prehistory. Now let's consider something fundamental. If all these remarkable creatures existed, if entire ecosystems rose and fell over millions of years, why don't we have more evidence? Why are there these enormous gaps? Here's the gentle truth. Fossilization is unbelievably, spectacularly rare. Think about every animal that passes away today. Every bird, every deer, every fish. How many of them will become fossils? How many will still exist as recognizable remains 10 million years from now? The answer is almost none. Effectively, zero. Because fossilization requires a perfect alignment of conditions that almost never happens. first, the organism must pass away in exactly the right place. Not on a hillside where the remains will scatter. Not in a stream where water will separate everything. Not in the open where sun and weather will gradually return everything to the earth. It needs to be somewhere it can be buried quickly, before natural processes do their work. Already we're down to maybe 1 in a million organisms that even reaches this stage. But that's just the beginning. Once buried, the organism needs to stay buried for millions of years, undisturbed, while chemical processes slowly replace organic material with minerals. This process requires specific groundwater chemistry, specific mineral content, specific conditions, and it needs to continue unchanged for millions of years. Even when everything goes perfectly, the fossilization process is selective. Hard parts like bones and shells might survive, but soft tissue, skin, muscles, organs, gone, completely recycled. Except in the rarest of circumstances, this means we're essentially working with skeletal frameworks, trying to reconstruct entire living organisms from their bones alone. Let your mind rest now. Imagine trying to understand modern elephants if all you had were their skeletons. Would you know about their trunks, their intelligence, their complex social structures, their ability to communicate through deep, rumbling sounds, not from bones alone? You wouldn't. Your whole body can be completely relaxed now, heavy and comfortable. Your breath flowing naturally like gentle waves. Sleep is so close, so welcoming. And we've only just begun listing the challenges. Let's say an organism beats all those odds. It passes away in the right place, gets buried quickly, stays buried, and successfully fossilizes. Now it needs to survive millions of years of geological changes because the Earth doesn't sit still. The Earth is constantly transforming its own history. Plate tectonics is the great recycler of the fossil record. Every year, tectonic plates drift a few centimeters over millions of years. Those plates move thousands of miles. They collide, creating mountain ranges. They split apart, opening ocean basins. And most significantly for fossils, they subduct. One plate slides beneath another, descending into the mantle where temperatures and pressures transform everything back to molten rock. Gone. Melted back into the Earth's interior, entire continents worth of fossils, entire epochs of evolutionary history simply recycled. The Pacific Ocean floor, for example, is almost entirely less than 200 million years old. Everything older has been subducted. Millions of years of ocean life, entire marine ecosystems transformed back to magma. But subduction isn't the only process that erases history. Mountain building crumples rock, layers, fracturing fossils. Volcanic eruptions bury fossil beds under new rock or heat them until remains are gone. Metamorphism, the transformation of rock under heat and pressure, can obliterate fossils by recrystallizing the very stone they're preserved in. Then there's erosion, the slow, patient wearing away of everything. Mountains rise, and immediately wind and water begin softening them. Every rainstorm carries away a little more sediment. Every freeze-thaw cycle cracks rocks apart. Every river carves deeper into ancient layers. Over millions of years, erosion can remove thousands of feet of rock, and with it, every fossil that rock contained. And here's what makes it even more interesting. The fossils we do find are the result of a fortunate reversal. Erosion has to remove just enough rock to expose the fossil layer, but not so much that it destroys the fossils themselves. Then, by pure chance, someone has to be in that exact spot during the brief period, maybe a few hundred years, when the fossils are exposed before erosion finishes its work. The odds are astronomical. Most fossils that survive fossilization and millions of years of geological activity never get discovered. They're buried under human developments, underwater, in remote regions where no one will ever look. They're exposed during a storm and eroded away before anyone sees them. They're found by people who don't recognize them and simply pass by. Professional paleontologists estimate that we've discovered less than 1% of all fossils that ever existed. Less than 1%. And remember, only a tiny fraction of organisms that ever lived became fossils in the first place. We're looking at multiple layers of improbability. 1 in a million organisms fossilizes. 1 in 100 fossilized organisms survives to the present. 1 in 100 surviving fossils ever gets discovered. For every fossil in a museum, there might be 1 billion organisms that lived and passed away without leaving any permanent trace. This preservation challenge gets even more complex when you consider environment. Some environments are wonderful for fossil preservation. River deltas, lake beds, coastal lagoons, places where sediment accumulates steadily and buries things gently, but mountains, forests, grasslands, these environments rarely preserve anything. An animal passes away on a hillside, and natural processes return the remains to the earth within weeks. 1 million years later, erosion might remove that entire hillside, and there's nothing left to find. This means entire ecosystems are nearly invisible to paleontology. We know far more about ancient coastal wetlands than we do about ancient mountains. Not because mountains were less important, but because mountains don't preserve fossils well. And soft-bodied organisms, they might as well be invisible as far as the fossil record is concerned. Jellyfish, worms, anything without hard parts They decompose completely within days or weeks. The exceptional fossil sites that do preserve soft tissue are so rare and so celebrated precisely because they're beautiful anomalies. The normal fossil record tells us almost nothing about soft-bodied life. This creates enormous quiet spaces in our understanding. Think about modern ecosystems as you drift. In any environment, soft-bodied creatures often outnumber organisms with hard parts by orders of magnitude. They form the foundation of food webs. But in ancient ecosystems, they're almost completely absent from the fossil record. We're missing entire levels of ancient life, entire groups of organisms that must have existed but left no trace. And behavior. Fossils can tell us what an organism looked like, roughly how it moved, sometimes what it ate, but how it communicated, how it raised its young, how it interacted with others, gone. Occasionally, we find trackways showing multiple animals moving together, suggesting social behavior. Sometimes we find nesting sites or burrows, but these traces are incredibly rare. Let yourself be completely surrendered to comfort now, your body knowing exactly what to do, your mind free to wander through dreams whenever it's ready. The numbers are humbling when you really consider them. There are somewhere around 300,000 described fossil species. That sounds substantial until you realize there are over 8 million species alive today. And life has been evolving for 3.5 billion years. Conservative estimates suggest that over 5 billion species have existed throughout Earth's history. We found fossils of 300,000 of them. That's about 0.06%. We're missing more than 99.99% of all species that ever lived. And for the species we have found, we typically have only a handful of specimens. Sometimes just one. Entire groups known from a single partial skeleton found in one location. We're trying to understand global ecosystems and evolutionary patterns from a sample size that would be considered inadequate in any other field of study. It's like trying to understand human civilization by examining 3 random artifacts from different centuries found in different countries. You might learn something, but you'd miss most of the story. Then there's the problem of changing sea levels over geological time. Sea levels have fluctuated dramatically during ice ages. When water is held in glaciers, sea level drops hundreds of feet. Coastlines extend far out onto what is now continental shelf. Then the ice melts and sea level rises, flooding those coastal plains completely. This has happened dozens of times over the last few million years alone. Every time sea level rises, it covers coastal ecosystems. Forests become seabed. Rivers disappear underwater. Later, when sea level drops again, these flooded landscapes are exposed to erosion. wearing away evidence even further. If any early human populations lived on these coastal plains during the ice ages, and there's every reason to think they did, then almost every trace of them now lies beneath the ocean, hidden under layers of sand, mud, and quiet shifting currents. Entire chapters of our story may be sitting out there, wrapped in silence. Today, more than 20 million square kilometers of shallow continental shelf lie underwater. Land that would have been dry during many ice ages. These drowned plains could hold ancient tool sites, migration paths, abandoned camps, or even early coastal settlements. But they remain out of reach, preserved beneath the waves like sealed time capsules. Marine archaeologists have begun finding hints of these lost worlds, not full civilizations, nothing so dramatic, but submerged forests, ancient riverbeds, and buried shorelines that once shaped human movement. In some places, stone tools have been recovered miles offshore, sitting in what used to be river valleys before the sea claimed them. This means that when we search for the origins of hominins on land alone, we are working with a map that's missing entire continents of evidence. What we see today is only the highest ground, the places that didn't drown, didn't erode, and didn't vanish. Everything else is either gone or sleeping beneath the ocean. This is why scientists speak of an archaeological blackout for early coastal populations. These humans may have relied on fishing, shoreline gathering, and marine resources, but their story lies underwater, untouched, quiet, waiting for the rare moment when technology becomes gentle enough and precise enough to uncover their traces. And so, what appears to us as a sudden leap in intelligence or a mysterious shift in behavior might simply be the result of missing chapters, long, slow, gradual developments that once played out along ancient coasts, now erased by rising seas. The record feels incomplete, not because early humans were rare or strange, but because the landscapes they walked upon are gone. Even today, satellite imaging of the ocean floor reveals winding channels, fossil rivers, that once carried fresh water across wide plains where mammoths grazed and early hominins likely traveled. These ghost rivers stretch for hundreds of miles beneath the waves, reminding us that the world we see today is only one version of Earth, a temporary version. And as the planet continued shifting through warm and cold cycles, new coastlines formed again and again. People moved with them, animals moved with them, cultures rose, faded, migrated, and adapted, all along edges of land that no longer exist. This constant redrawing of the world carved deep gaps in the fossil record. Bones decay, tools wash away, campsites vanish. Beneath rolling tides, what survives does so by chance, not design. Which means that much of prehistory is not lost due to mystery, but because Earth itself has always been in motion, and every movement, every glacial drop, every rise of the sea quietly erased another chapter of our beginnings. This is why researchers refer to early human evolution as a tapestry with threads missing, not because the story isn't there, but because the fabric has been worn thin by time. What remains are the strongest strands, a handful of bones, a chipped stone, a preserved footprint, a layer of ash, enough to hint at a story, but never enough to complete it. When early humans lived near lakes or rivers, seasonal flooding could sweep away entire settlements. What might have been a thriving camp for generations could disappear in a single storm, leaving behind only scattered fragments buried deep beneath sediment. In places where volcanic activity was common, ash layers could both preserve and destroy evidence. A thick ash fall can lock footprints and tools in place for hundreds of thousands of years. But lava flows can erase everything beneath them. Nature chooses what stays and what fades. Even fossils themselves require incredible luck. For a bone to become fossilized, it must be buried quickly, protected from scavengers, shielded from rain, and left undisturbed for hundreds of thousands of years. Most bones never get that chance. They crumble long before scientists ever see them. This means that when we look at the prehistoric record, we are seeing less than 1% of everything that ever existed. The rest vanished into soil, washed into rivers, dissolved in rainwater, or was simply never preserved at all. Whole species may have lived and gone extinct without leaving a single fossil behind. Entire branches of our evolutionary tree may be invisible to us, hidden by chance and time. What we call mystery is often just the absence of evidence. And yet, even with these gaps, patterns emerge. We know early humans spread across Africa, then beyond. We know they adapted to deserts, forests, and mountains. We know they shaped stone, explored coastlines, and followed herds through open plains. These movements were slow, quiet, and intertwined with the rhythms of Earth itself. Glaciers advancing, forests expanding, savannas drying. Human evolution flowed with the planet's heartbeat, not in sudden leaps, but in gentle, gradual shifts. And this brings us back to the time gap that puzzles so many researchers. The missing period isn't a single slot in history. It's a constellation of lost moments, scattered by erosion, buried under oceans, erased by climate, hidden under volcanic layers. Instead of imagining a dramatic event that erased our past, it may be more accurate to imagine countless small erasures happening slowly, naturally, over millions of years. Not a catastrophe, but a quiet fading. Consider that even today, coastlines continue to change. In some places, the sea is rising, swallowing lowlands. In others, land is lifting slowly due to tectonic motion. What disappears today will become the mystery of tomorrow. If future scientists were to study our world millions of years from now, they would also see gaps. Our oldest cities might erode. Our coastlines might vanish underwater. Only fragments would survive to tell our story. This perspective softens the idea of a mysterious missing age. Instead, it becomes an invitation to understand how fragile evidence really is, and how much patience is required to piece together the world shaped by wind, water, and deep time. Some of the most promising discoveries today come not from deserts or caves, but from riverbeds, coastlines, and submerged shelves as technology grows gentler, capable of scanning beneath layers of sand without disturbing them. We may one day uncover new chapters waiting quietly below. But for now, we live with the gaps, blank spaces in the timeline that remind us how ancient, how vast, and how dynamic Earth truly is. These gaps are not failures in our knowledge. They are natural pauses in a story written by a planet that never stands still. And sometimes those pauses are beautiful. They allow imagination to drift softly through time. They let us picture early humans walking across wide plains that no longer exist, or sitting beside rivers that now flow beneath the sea, or watching stars from hilltops that have long since eroded away. In this way, prehistory becomes less of a puzzle to solve and more of a gentle reminder that most of Earth's past is silent, patient, and hidden, a story told in whispers. And as you rest now, letting your mind wander softly through these ancient landscapes, you might feel a sense of spaciousness, a quiet understanding that the world is older, deeper, and more mysterious than we can ever fully grasp. The gaps are not errors. They are part of the design. Nature leaves room for wonder, and in that wonder, in that peaceful unknowing, we find something calming, a sense that not every answer must be discovered tonight. Some things can remain gentle mysteries, drifting in the dark beneath oceans or buried beneath soft layers of time. So as you settle deeper into rest, imagine those lost coastlines, those quiet plains beneath the waves, those ancient paths walked long before memory. They are still there, silent, untouched, and beautifully distant. Let yourself drift with them, slowly, softly, as the long story of Earth continues to breathe beneath you.